Dear students, welcome back to my YouTube channel. Today I would like to discuss with you from the topic phenol, structure and nomenclature, its preparation and acidity, that is substituent effect. So a phenol contains a hydroxyl group which is directly bonded to a benzene ring. Phenols have widely varying role in nature, from hormones and antibiotic and to the blistering agents of poison ivy. Phenol itself and its isomeric resource, that is ortho, meta, and paracresol, are found in coal tar and petroleum, and several compounds like thymol and vanillin are important constituents of thyme and vanillin beans. And the thymol, it is a type of phenol, 2-isopropyl 5-methylphenol. Vanillin is also a phenol for hydroxy-3-methoxybenzaldehyde, which is naturally occurring. And now let us discuss the structure and bonding in phenol. And this is the structure of phenol, and this structure of methanol. And you can see that CO bond, that is the bond distance, is 136 picometer, which is shorter than this carbon oxygen bond in methanol, that is 142. So what is the reason for that? As you already know, the bond to sp2 hybridized carbons are shorter than sp3 hybridized carbon, that is, this one is sp3 hybridized, and this case, this one is sp2 hybridized carbon. And moreover, there is a resonance in phenol. That is the reason for shorter carbon oxygen bond distance phenol, which is as attributed to partial double bond character that result from conjugation of this unshared pair electron on oxygen with the aromatic ring, and which is shown here. And the unshared pair on oxygen, these are in conjugation with this benzene ring, and the first one is the most stable Lewis structure for phenol, and these are the resonance structure of phenol. And you can see there are three other structures, that is dipolar in nature, dipolar resonance forms of phenol. And you can see in the resonance structure, CO bond are in double bond, are having double bond character. That is the reason for shorter bond distance or bond length for CO bond in phenol. Now let's see the nomenclature. Substituted phenols are named either as derivative of phenol or as benzenol or by their common name. More highly substituted compounds are named as derivative of phenol. And numbering of ring begins usually at hydroxyl substituted carbon. We have to start from hydroxyl group and proceed in the direction that gives the lower number to the next substituent. And finally, if you have more than two substituent or one substituent, substituents are cited in alphabetic order. For example, for chlorophenol, this you have to start numbering from here, 1, 2, 3, 4. This is for chlorophenol, and its common name is parachlorophenol. And this one is 2-nitrophenol, and its common name is orthonitrophenol, and IUPAC name of third compound is 3-bromophenol, and it is metabromophenol. And if you have a methyl substituent here at ortho position, it is called orthocresol, and to meta position it is metacresol, and it is paracresol. And IUPAC name is 2-methylphenol, and here this one is 3-methylphenol, and this 4-methylphenol. And if you have two hydroxyl group, it is benzene thiols, and the common name for benzene thiols are different. In the case of 1,2 substituted thiol, it is called catechol, and 1,3 substituted disubstituted compounds are resorcinol, and 1,4 benzene thiol is hydroquinone. And next example, if you have more than one substituent, and that is 1-methyl and chlorine, and you have to start number from here, hydroxyl group, and you have to go this direction. The reason is the substituent should get lowest number. and you have two substituent here. One is methyl group, another one is chlorine. So you have to start in alphabetic order. That is 5-chloro-2-methyl phenol. Next one is preparation, and you can prepare from cumene, and this is a wonderful method converting to relatively inexpensive organic compound, that is benzene and propene, into two more valuable one, that is phenol and acetone. Both are very valuable industrially. The only other substance consumed in the process is oxygen from the air, and most of the worldwide production of phenol is now based on this method. And this synthesis starts with Friedel-Crafts alkylation of benzene with propene, and it produces cumene first. That is, cumene means the isopropyl benzene. So benzene with the isopropene, it gives cumene. And the second step is cumene is oxidized to cumene hydroperoxide, and this is cumene in the air at high temperature. It become oxidized to, and it become cumene hydroperoxide. Finally, when treated with 10% sulfuric acid in acidic medium, this hydrogen peroxide undergo a hydrolytic rearrangement, and it form phenol and acetone. And second preparation method, you can prepare phenol from benzene sulfonic acid. That is pyrolysis of sodium benzene sulfonate. In this process, benzene sulfonic acid is reacted with aqueous sodium hydroxide, and it forms a salt. That is, here benzene sulfonic acid in the presence of aqueous sodium hydroxide, it forms salt. You can see it here, and the resulting salt is mixed with solid sodium hydroxide, that is this one, and it is fused at a high temperature. We get a sodium phenoxide, and this product, which is finally acidified with aqueous acid to yield phenol. The final one, the acidity of phenol, that is substituent effect, and phenols are more acidic than alcohol, but at the same time less acidic than carboxylic acid. Carboxylic acid have ionization constant, that is Kf of approximately 10 raised to minus 5, that is pK will be around 5, and Ka of alcohol are in the range 10 raised to minus 16 to 10 raised to minus 20, and its pK will be 16 to 20. And Ka for most of phenol is in between these two, that is 10 raised to minus 10, and its pK will be around 10. And alcohols and phenol, there is a difference in charge localization of negative charge. Usually when you put the ethanol or alcohol or phenol, any alcohol in acid, an acid, it dissociates and it furnish H plus. So it depends on the number of H plus ion produced, that will be more acidic. So that depends on the stability of this conjugate base, that is ethoxide. Usually if it is stable, it will be, dissociation will be more favored. But in the case of ethoxide, the negative charge in this oxygen is localized on oxygen and is only stabilized by solvation. But at the same time, phenoxide, this negative charge is in phenoxide is stabilized by solvation as well as by electron delocalization. So the negative charge on this oxygen or minus is delocalized over the aromatic ring like this. So this is the these are the resonance structures of phenoxide ion, and because of this stability of its conjugate base, this forward reaction will be more favored. So it will be more acidic. So the acidicity depends on the stability of its conjugate base. Similarly, another example, you can see here cyclohexanol and phenol, and the cyclohexanol is less acidic when compared to phenol because here there is no resonance structure is possible. All right, and so next one is substituent effect. In the case of the phenol and metacresol, when you compare the acidity of paracresol, that is methyl group at meta and para position, you can compare the pKa value. And in the case of phenol, it is 9.95. When you have a meta substitution at of methyl group is pKa is decreased. That is acidicity get decreased. So in the case of methyl, if it is at para position, its acidity get decreased again. And but at the same time, if you have a chloro substituent at this meta position, the pKa value of phenol get increased. And if you have a para chloro substituent at para position, the pKa value get increased. So what are the reason for that? Ring substituent, particularly halogen and nitro group, have marked effect on acidicity of phenol because it has two role here. That is inductive effect and resonance effect, the two main factors that decide the acidicity. So in this case, nitro and chloro, it has an inductive and resonance effect. But at the same time, in the case of metacresol and paracresol are weaker acid than phenol, and metachloro and parachloro are stronger. The reason for this weaker acidity of cresol is due to this negative charge in this resonance structure. The negative charge, the polarization of this CC bond is by electron releasing inductive effect of this sp3 methyl group, it destabilizes this contributing structure, and that is this negative charge, it destabilizes the negative charge because of the plus I effect of methyl group. But at the same time, if you have a chloro or nitro group here, it stabilizes at the negative charge. And that you can see here, phenol, if you compare the acidity of phenol and methanitrophenol or paranitrophenol, you can see that this negative charge is stabilized by resonance, or this negative charge is delocalized over the nitro group like here. So the delocalization of negative charge onto oxygen further increases the resonance stabilization of phenoxide ion. That is why 2,4,6 trinitrophenol, that is picric acid, is highly acidic. That is, its pKa value is 0.38, and it is the more acidic than even hydrogen sulfonate ion or phosphoric acid ion. So this is due to the combined effect of resonance and inductive effect. And in summary, phenol, we have learned how to do the nomenclature and structure and bonding in preparation from cumene and Benzene sulfonic acid, and the acidity of phenol also discussed, and effect of substituent on acidity. Okay, thank you for watching.